Amides can be hydrolyzed to carboxylic acids under acidic and basic conditions. This video will be about looking at the mechanism under acidic conditions. The reaction is very slow and requires quite a bit of heating to work, and that's because the amide is the most stable of the carboxylic acid derivatives, so the activation energy is quite high to get it to react. Let's look at the mechanism of hydrolysis. So we are starting out with an amide, and I've drawn a primary amide, but it could be a secondary or a tertiary amide. There is no limitation where that comes into play. So we're treating this with a strong acid, such as hydronium. And there can be a proton transfer onto the amide. If we look at the resonance contributors of the amide, and we'll just draw the allylic lone pair pattern. We'll see that the oxygen has a partial negative charge. So that will be the atom that picks up the proton from the acid. Once that happens, water can attack. But again, the amide is so stable that the activation energy for this step is high, and that's what the heat is why the heat is necessary. This is the product after water has done its nucleophilic attack. In order to get to a carboxylic acid, we need to kick out the amine, but it first needs to be protonated so that it's a good leaving group. Before we can protonate it, however, we need to deprotonate the positively charged oxygen. We'll use water as the base in this reaction. So once the proton is removed from the oxygen, it can be added to the nitrogen. Now the protonated nitrogen is a good leaving group, and it can leave. With the loss of a leaving group, we can go ahead and show a resonance arrow. So ammonia left in the previous step. So that's the best base in solution now. So the final proton transfer will show with ammonia. So the final product in this case is the carboxylic acid and also ammonia. Ammonia's pKa is about 9 to 10, and the pKa of the acid here is -2 for hydronium ion. So there's a driving force to form the weaker acid in the reaction.